All right, next we want to talk about the natural logarithmic function and how it relates to integration. So first off, let's just talk about the natural log function. And we're going to start off with this question. Find an antiderivative of the function using the power rule for integration. So here we have the indefinite integral of 1 over x dx. So first thing we would want to do is change this to our negative exponent. So this is x to the negative 1 dx. And now if we're going to use our power rule, remember this is x to the n plus 1 over n plus 1. So if we add 1 to negative 1, we get a 0. And then we divide by that n plus 1, so we divide by 0. And anything to the 0 power is 1, so this becomes 1 over 0. And you can see that this is going to be undefined. Okay, so if we're looking at the general power rule, the indefinite integral of x to the nth power is x to the n plus 1 over n plus 1 plus c, as long as n does not equal negative 1. Okay, because if n is negative 1, then the general power rule is undefined. So the answer to this question is neither algebraic nor trigonometric. And just because we get an undefined answer doesn't mean there isn't an answer. And in math, a lot of times when we get something that's undefined, we create new math to describe what's happening. So we need another class of functions to describe this integral. Here enters the natural logarithmic function. Okay, now we know that this integral must exist because here is the graph of 1 over x, right? And if we just took any integral, so this would be like the integral from 1 to 2, you can see that this indeed does have an area. So it just doesn't mean that this is undefined. There is an answer to it. It just is not going to be found using the power rule. So if we were to think about the natural log function and we wanted to find its derivative, so remember the derivative with respect to x of ln of x equals 1 over x. And if I wanted to find the integral here, remember we can use the second fundamental theorem of calculus because the derivative of the integral is just the inside. And so we would see this sort of cancellation here of the derivative of the integral, leaving us with just the natural log of x. Okay, and so this actually gives us the definition of the natural logarithmic function. So ln of x equals the definite integral from 1 to x of 1 over t dt. And here x has to be greater than 0, so it doesn't make sense for the natural log function to be less than 0 here. So instead of using the power rule here, the antiderivative of 1 over x is actually just the natural log of x. So in this example it says use properties of integration and the definition of natural log to determine where the natural log of x is positive, negative, and 0. So first off, we want to find the natural log between 0 and 1. We want to tell whether this is positive or negative. Okay, so I'm going to erase this here, and we're going to use this idea of the integral to help us answer this. Okay, and so we're just going to test out something in this interval, and let's just try natural log of 0.5. So using our definition now, we're going to have the integral from 1 to 0.5 of 1 over x dx. And if we were to look at what's going on here, so we're going from 1 to 0.5, and so we get this area right here. And if we remember our properties, now we're going backwards, and so we would switch this around and be negative the integral from 0.5 to 1 of 1 over x dx. So looking at this area is going to be positive, but we have to take the negative because we had to switch our limits of integration. So this answer is actually going to be negative. Okay, let's take a look at the natural log of 1. We'll clear that out. So the natural log of 1 is going to be the integral from 1 to 1 of 1 over x dx. And if we look at this, our limits of integration are equal, and so there is no area here, and we know that this would give us 0. So the natural log of 1 equals 0. And if the natural log of x is greater than 1, okay, let's just try like 2. So let's try the natural log of 2. So that would be out here. We're looking for this area. So this would equal the integral from 1 to 2 of 1 over x dx. And you can see here that this area is positive, and so this is going to give us a positive answer. Okay, so we were just using the integral here to determine whether the natural log was negative, 0, or positive. And you can see if it's between 0 and 1, it's negative. If it's 1, it's 0. And if it's greater than 1, it turns out to be positive. Next, we want to use the first and second derivative of the natural logarithmic function to describe the graph of the natural log function. So here's f of x equals ln of x, and you can see this graph right here. And a graphing calculator can do this. But what we want to do now is find the derivative here. So what's the derivative of f of x? Well, we know it's going to be derivative of natural log is 1 over x. Okay, and so using our first derivative test, notice that ln of x always has to be positive. So if I plug any positive number in here for x is greater than 0, I'm going to get a positive number. So that means that this function is always increasing on the interval x is greater than 0. Okay, now let's go ahead and find our second derivative. So the second derivative of this, well, remember, it would be the derivative of x to the negative 1, so we would get 1 over x squared. And now, if we plugged in that x being positive, this is always going to give me a negative. So if we use our second derivative test, it's always negative. And so what that means is it's concave down over the whole interval x is greater than 0. Okay, so here you can see that our function is constantly increasing, but that it is concave down. Now, a couple other properties of the natural log function is the domain is from 0 to infinity, which we've been talking about, but the range goes from negative infinity down this way to positive infinity up this way. The function is continuous and increasing, and it's also 1 to 1. And the graph is concave downward. Next, we're going to relate the log function to the number e. Okay, so just recall real quickly that log base b of x equals y really means that b to the y equals x. So if we look at log base b of b, that's going to equal 1. Okay, because we have to think b to the what power equals b. Well, b to the first power equals b, so that means this has to equal 1. So let's apply that now to log base e of x, which equals the natural log of x. Okay, so log base e and natural log are the same thing. So what we're going to do here is substitute x with e. So log base e of e would equal the natural log of e. And if we look at log base e of e, we can use the same thought of log base b of b, that it equals 1. Okay, because e to the first power equals e. Therefore, the natural log of e has to equal 1. So what that tells us, the definition of e, is that the letter of e denotes the positive real number such that the natural log of e equals the definite integral from 1 to e of 1 over t dt, and this equals 1. So in other words, what we're doing is we're taking the function 1 over x, and we're finding the area under the curve from 1 to e such that this area right here equals 1. So it's kind of a backwards approach. So e is that limit of integration that gives us an area of 1 for the integral. So now we want to evaluate some logarithmic expressions. Okay, so natural log of e to the 0 power, notice we can rewrite this as being 0 natural log of e. Well, 0 times anything equals 0. If we wanted to do natural log of e to the first power, that would just be 1. If we wanted to do the natural log of e to the second power, this is going to be 2 times the natural log of e. Well, the natural log of e is 1, making this 2. Now, if we want to find other natural logs of other numbers, like 232.1, for this we are going to use a calculator, and you would just type it in, natural log of 2, and that's approximately 0.693, and the natural log of 32, which is approximately 3.466, and the natural log of 0.1 is negative 2.302. So make sure you try those out in your calculator and that you do come up with these numbers for the natural logs. All right, let's move on. All right, next we want to talk about the log rule for integration and actually integrate some of these here. So it says let u be a differentiable function of x, and it says the integral of 1 over u du equals the natural log of the absolute value of u plus c. Notice it has to be absolute value because we can't take the natural log of a negative number. Or alternatively, we can also think of this as u prime over u dx. So this integral is the natural log of the absolute value of u plus c. So again, we're just kind of undoing that thought. Remember, if we take the derivative with respect to x of the natural log of u, that was u prime over u. And so now we're just going backwards. Okay, so if we take this integral, this is kind of what we get right here. Okay, so we want to use the log rule for integration in this function right here. And first thing we want to do is take out that constant multiple. So we'll rewrite this as 2 times the integral of 1 over x dx. And this is the most simple form. So here the integral of 1 over x dx is the natural log. So this is going to be 2 times the natural log of the absolute value of x plus c. Okay, so this case came out nice and perfect to the 1 over x. Now the trick is going to be recognizing quotient forms of the log rule. Okay, in other words, what we're looking for is u prime over u. That's going to be our ticket. So looking at this, we want to see what can we let u equal. So a lot of times, just try to let the denominator equal u. So if we do that here, we get x cubed plus x. And then let's go ahead and find u prime, which would be 3x squared plus 1 dx. Okay, and let's see if we can find u prime over u in this form. Here I would see my u prime. So here we have the integral of u prime over u. And so we can go straight to the natural log of the absolute value of u plus c, and then substitute u back in. So this really equals the natural log of the absolute value of x cubed plus x plus c. Okay, so for letter B here, we're going to let u equal tan x, and we know u prime is secant squared x, and so you should be able to see here u prime over u. And so this then becomes the natural log of the absolute value of tan x plus c. All right, in example C here, we're going to let u equal x squared plus 2x, following with the denominator there, and u prime would be 2x plus 2. And if we look, we only have an x plus 1 on top, so we don't quite have u prime, but if we multiplied the numerator by 2, then we would have our 2x plus 2. And to keep this balanced then, we have to multiply it on the outside by 1/2. Okay, so we really have 1/2 times the integral, and we'll distribute that 2 to get 2x plus 2 over x squared plus 2x dx. Now we have u prime over u, and so our final answer is going to be 1/2 times the natural log of the absolute value of x squared plus 2x plus c. All right, for letter D, one more example here. So u we're going to let equal 3x plus 2, and u prime is going to equal 3. Notice we don't have a 3, so we need to multiply by 3 on the inside and 1/3 on the outside. So our final answer is going to be 1/3 times the natural log of the absolute value of 3x plus 2 plus c. All right, next we want to look at an example of using the log rule with a change of variables. And if you'll notice in letter A, this is very much the same as what we just did here in the previous example. So if u had been 4x minus 1, u prime would have been 4, and notice we're missing the 4, so we'll add on the inside and put a 1/4 on the outside, and so we simply go straight to 1/4 natural log the absolute value of 4x minus 1 plus c. In letter B, we have a quantity squared. So we're actually going to let u equal just the x plus 1. And u prime is going to equal 1 dx. And notice I've been a little bit lazy about all of these dx's here. They should technically all have them, okay, so that we actually have u prime in there. And if you look up here, we have something that says 2x. And so we're going to use an idea where we need to change that variable to all be in terms of u. So x equals u minus 1. So you can notice right here, if we subtract 1 from both sides, we get x equals u minus 1. Okay, so let's go ahead and change this variable now into everything with u's. So we're going to get 2 times u minus 1 over u squared and du. Okay, so we'll factor out this 2 here. So we'll get 2 times the integral of u minus 1 over u squared du. And then let's break up the u minus 1 over u squared. So it's 2 times the integral of u over u squared minus 1 over u squared du. And now we can rewrite this as 2 integrals. So we'll just go 2 times the integral of u over u squared is 1 over u du, and then minus 2 times the integral of u to the negative 2 du, so that we can integrate that. So let's integrate our first one. That's going to give me 2 times the natural log of the absolute value of u minus 2, that's the u to the negative 1 over negative 1 plus c. And let's clean this up a little bit. So we get 2 ln absolute value of u, and negative negative, so plus 2, and then u to the negative 1 is actually 1 over u plus c. And now let's go ahead and substitute x plus 1 back in for u. So our final answer here is going to be 2 times the natural log of the absolute value of x plus 1 plus 2 over x plus 1 plus c. Alright, so let's move on. Next we want to do an example where we need to use long division before integrating. So here, if we look at the u and du, if we let the bottom just be u, the du would be 2x, and you see we have an extra x squared here, so it's going to be a little weird. So a lot of times we want to actually try to divide this before we integrate. Okay, so let's use long division here. So we're going to have x squared plus x plus 1 divided by x squared plus 1. And so x squared goes into x squared one time. Okay, so if we do 1 times x squared plus 1, we get x squared. And then if we line it up, the 1 would go right here. And then remember, we have to subtract this. And so I want to change all of the signs. And And when I change signs, I circle it so that I know that I actually changed the sign. And let's subtract here. So x squared minus x squared, you get 0. X, you have nothing to do there, so you just bring down your x. And then 1 minus 1 is also 0. So all you're left with now is x. And so x squared doesn't go into x anymore, so all you have to do is go plus the x divided by x squared plus 1. Okay, so you still have x divided by x squared plus 1. And so let's rewrite this integral now as the integral of 1 plus x over x squared plus 1 dx. Okay, and let's separate these into two integrals here. So the integral of 1 dx plus the integral of x over x squared plus 1 dx. And now if you look here, we can let u equal x squared plus 1, and u prime would be 2x. So we have u prime over u if we had a 2 here and a 1/2 here. Okay, so now we can go ahead and integrate all this. The integral of 1 dx is just x. And then here we're going to have 1/2, and then this is u prime over u. So it's the natural log of the absolute value of x squared plus 1 plus c. Now one note here. Since this is x squared plus 1, can x squared plus 1 ever be less than 0? Okay, so this is a question. Can x squared plus 1 ever be less than 0? Well, the answer is no. There's actually no real roots. So what we do here, instead of having the absolute value sign, is we change it to parentheses. Okay, because this cannot happen. So instead of having absolute value here, you're just going to see this in parentheses. Alright, in our next example, we want to evaluate a definite integral. So here's our definite integral from 0 to 3 of x over x squared plus 1. So again, we're still going to do the same u, let that be x squared plus 1, and du is going to be 2x dx. And so you can see we're missing a 2 here, so we'll add a 1/2 on the outside. And let's go ahead and integrate this. So we have 1/2 times the natural log of the absolute value. Well, we don't even need absolute value anymore because it's x squared plus 1. And we want to evaluate this from 0 to 3. Okay, so now we're going to apply the fundamental theorem of calculus here. So we're going to get 1/2, and we can actually factor this outside, times the natural log, and we'll substitute in 3, so 3 squared plus 1. And then we're going to substitute 0, so the natural log of 0 squared plus 1. And so this is 1/2 times the natural log of 10 minus the natural log of 1. Okay, and we know that the natural log of 1, remember, it's going to be from 1 to 1, and so this actually equals 0 here. So we're left with 1/2 times the natural log of 10, and remember the exponent can come up here, so this is really natural log of 10 to the 1/2, which is the natural log of the square root of 10. And either way, if you put this into your calculator, you're going to get about 1.151. Okay, so that's how we're going to evaluate our definite integrals using natural logs. And we just have a couple extra examples here. So here we have the integral of 1 over x squared dx. So let's try to let u equal x squared, and u prime would be 2x dx. Now we can never add an x in here, and so this is actually not going to work. And we've been using natural log and looking for the u prime over u, but in this case, why don't we just use the power rule? Hey, that's totally going to work. And so this is going to equal x to the -1 over -1 plus c, which is -1 over x plus c. So be on the lookout. We can always use the power rule when this exponent is not 1. Okay, so in j here you can see that we do have a power of 1. Okay, so we can't just use our power rule. Now again, what we always want to do is divide this out first. So this is the integral of x cubed over x plus 2x over x plus 1 over x dx. So go ahead and divide that out first, and then you can simplify. So this is really the integral of x squared, because x cubed over x. And we'll split this into separate integrals. And then 2x over x is just going to be 2. And then plus the integral of 1 over x dx. And then we integrate each one separately. So here we get x cubed over 3. And then this one becomes 2x. And this last one becomes the natural log of the absolute value of x. And finally plus c. So divide out first if you can. Now letter K, this one's a little bit tricky. We have 1 over x times the natural log of x. So if we were to let u equal the natural log of x, and now what does u prime equal? Well, 1 over x dx. So now you can see here that this 1 over x dx is really our u prime over u. So this is really 1 over x over the natural log of x dx. And so we do indeed have our u prime over u. Okay, so we know this is going to be the natural log of the absolute value of u plus c. And so then we can just substitute right back in for u. And we get the natural log of the absolute value of the natural log of x plus c. Now notice we keep the absolute value here because natural log can be negative. And in our final example, so here we have a polynomial over another polynomial, and so we want to use long division. Okay, so we get 3x to the 4th plus 2x squared plus 4x minus 8 divided by x squared plus 2. So x squared goes into 3x to the 4th, 3x squared times. So we get 3x to the 4th, and then plus 6x squared. And now we subtract. Okay, which leaves me with 0 here, and negative 4x squared plus 4x minus 8. And now we say x squared goes into negative 4x squared how many times? Well, negative 4 times. So now we get negative 4x squared, and then negative 4 times 2 is negative 8. And we got to change our signs. Okay, and if we subtract that there, we get 0, and we would get plus 4x, and then negative 8 over 8 is also 0. So this is now going to be plus 4x over x squared plus 2. Okay, so now we need to take the integral of 3x squared minus 4 plus 4x over x squared plus 2 dx. And so this one would give me x cubed, well, 3x cubed over 3, and the 3's cancel, of course. The negative 4 gives me negative 4x. And then this one here, if I let u equal x squared plus 2, du would be 2x. So here, what we want to do is rewrite this as 2 times 2x. And so now you can see I have u prime is 2x, and then we just have this extra 2 on the outside. So this is going to be plus 2 times the integral of 2x over x squared plus 2 dx. Okay, and so our final answer here is going to be x cubed minus 4x plus 2 ln of the absolute value of x squared plus 2, which is always positive. So I'm just going to put that in parentheses, and then plus c. Alright, so that is the natural log and integration.